So I have finished off my fast inverse square root algorithm design within Logisim. That is, I've built up a digital circuit. Now when I say a digital circuit, it's really a kind of pseudo digital circuit because I am using the Logisim primitives that are available to me, and it's not necessarily, in fact it isn't actually how a circuit would be designed in reality, but it does give us a good halfway house between the mathematics and the actual realization of a digital circuit. Now, when we look at the how we actually realize the digital circuit, that's another whole course and a whole different ball game altogether. For the moment, we're happy to be able to get results with this little tool called Logisim, and it gives us enough of an idea or an indication as to how these circuits work. So let's have a look at the circuit just now in Logisim. I'm not going to talk it through all of it in great details here. I've actually got quite a lot of stuff to get through. I've been busy over the weekend and I've had to adjust the design that I was intending to use, and I've got a few other things to add in. So let's crack on. We'll have a look at the circuit just now. So this is Logisim here, where we design our circuits. I've got about 10 or so circuits already designed over the last 5 days. I'm going to use 2 other circuits which I have designed in previous courses. So the first one is a 32-bit floating point adder and subtractor, and the other one is a 32-bit floating point multiplier. Now, if you're interested in how I designed these, I've got a couple of courses covering all of the mathematics, and from the mathematics moving on to the actual digital designs. So what we have here at this top level here is the actual divide circuit. You can see it's called divide. Now the actual divider is in here. So it takes a value of x and a value of y, and it produces the output x divided by y in 32-bit floating point. Now I have a little RAM here, here and here, so a RAM for one of the inputs and the second input, and a RAM for the output. So it means I can put in the values in here and I can put a value in here, and because the circuit here is purely combinatorial, that is, we don't have any clocks pulses here, so we're not having to clock anything through, so the answer will actually come out instantaneously. It will come out here, and I can put a second value in here and here, and I can clock it on to that second value. So it allows me to put lots of different values in here and to clock through to get the output. But we're only going to look at one particular value in this video. So we're going to look at 250 divided by 25. So 250 is 437A, 1, 2, 3, 4. And the 25 is 4, 1, 2, 0, 0, 0, 0, 0. Okay, now you'll notice here it takes a few seconds for this to pass through. I did have problems with this circuit and it was oscillating, so it's hardly surprising when it's a huge combinatorial circuit here, and Logisim is just a freeware bit of software, although it's still very, very good. So it was oscillating a bit, so I had to adjust some of the internal mechanisms here within Logisim to get it running smoothly. But here's the answer here. Now the correct answer, of course, is 250 divided by 25, which it should be a value of 10. Okay, so 25. So now the answer should be 10. So 10 in our 32-bit float is actually, if you look at the bottom here, it's actually 41C80000. Okay, so you can see we're actually quite close. We're at 41C7, and this is FF37. So if this was FFFF, we would only be in effect one out. Now, if we put this number here into a conversion tool, we'll find out that it actually gives a number 24.99 9617. Okay, so we are correct to 1, 2, 3, 4, 5 significant figures. So that's just the first one. I just wanted to quickly show you that. Now, I'm not going to go through the circuit in detail, but let's have a quick look inside. So we get into the circuit here, and you can see we've got our fast inverse square root and also the Newton-Raphson. Okay, so the Newton-Raphson's in here, and whenever we're going to do the final value for the multiplication, we have to run through the multiplication twice, because in effect we're working out the 1 upon square root times 1 upon square root in order to get just the 1 upon the value of x. Now within here we're going to have the fast inverse square root, and we're going to have the Newton-Raphson. Okay, so here's the fast inverse square root circuit here. Okay, now again I'll talk through in detail. What tends to happen is if I try to explain everything, the video could go on for 2 or 3 hours. Okay, so that is the basis of the fast inverse square root circuit. Now let's head up and we will head back into here. Now you can see here the Newton-Raphson. If I click in here, I'll make it a little bit bigger. It's relatively self-explanatory. These are the steps we go through. We go through the xi squared, and then we multiply it by the value of our y, multiply it by 0.5, and then we take it away from 1.5, and finally we multiply it by yi. So this is a Newton-Raphson equation. We've seen this in a previous video, but I just rewrote it so that it doesn't actually include any division term. Okay, so it's just the same as the Newton-Raphson we've seen in a previous video, just written in a different format. And all we have in here are the multipliers. So this is a multiplier, multiplier, multiplier. That's an add and subtract, and this is a multiply, and it just works through this little mathematical equation. Now I'll just quickly get in here because there's a lot of detail in this, and I'm not going to talk through this obviously, but this is the floating point multiplier. Okay, so this is a multiplier circuit here. Now I've got an entire course where I talk through how to design this floating point multiplier if you're interested. So we can go for there, and I'll quickly just drop into the add and subtract so you can see that as well. So there's only one add and subtract, so this is the add and subtract here. I can drop into it, and you can see again I've got a full course on how to design this add and subtract unit if you're interested. So I'll go ahead and I'll put in the square root. Okay, so we've looked at the division, so we'll look at the square root next. Okay, so the square root uses the same sort of process. We've got the fast inverse square root and the Newton-Raphson here, and we've got one multiplier. So again, I'll put in two numbers. So I'll put in 100 divided by 10. Okay, so if I come in here and the 100, let's see the value. No, actually, we'll put in 25 divided by 5. Okay, so 25 is going to be value of, well, actually the top level square root. This is the one we want to go to. So we'll get in here, simulate, reset, right, and we're ready to go. So we'll put in the number 25, which is 41C81234. Okay, so the correct number for this, obviously 25 divided by 5, the square root of 25 is a value of 5. Now the correct value should be 40, and I'll make this a little bit bigger so you can see it. So the correct value should be 40A and then 00000. Okay, and we're getting this answer here. Now this answer here actually in our the decimal version of this 32-bit float is actually 4.999947. Okay, so we're getting it correct to 1, 2, 3, 4, 5 significant figures. Okay, so again, it's a decent approximation. So I just wanted to show you these here, just to show you that it does actually work. If I drop down in here, again, we've got, as I showed you a second ago, the fast inverse square root algorithm and the Newton-Raphson here and a floating point multiplier. So that's just a quick video, just to let you know that I have actually designed all of this. It does work. Initially, I had some problems with the circuits oscillating, but I've had that before when using Logisim. You know, I am building quite large combinational circuits. I mean, probably larger combinational circuits than you would tend to see in reality. But it does work. We are getting the right answers. I can work out the division and also the square root using the fast inverse square root algorithm. So over the next couple of days, I'll put out a few more videos and I'll cover the circuits and I'll cover exactly how I went ahead and designed this. And I'll also make the circuit available to you as well if you want to have a little play with it. Now my intention was to use this within the actual floating point unit for our design a CPU 4, which is the math coprocessor. Now I've not decided whether to use this or not, and the jury's still out for the moment. I would have to check and see what it's like over a broader range of values. I do have one other person, my good friend Timothy Morgan, who has built the circuit and tested this. He believes it's inaccurate at low values, so that would be something that'd be interesting to look at. But I will cover some more stuff over the next couple of videos. So thank you for listening. I'll get you on the next video. Goodbye.